Welcome to Fresh Concrete. This is one of a series of online talks produced through partnership between the Concrete Centre and the Building Centre. And it's to showcase some of the innovative uses and manufacture and types of concrete that are being developed. So my name is Elaine Tugard, I'm Head of Architecture at the Concrete Centre, and I have been delighted to have the opportunity and the challenge to help select the new concrete technologies featured in this series. The underlying theme that runs through all of these talks is innovation, and innovation that addresses climate change mitigation and the adaptation needs of the built environment today. So this session is on innovative concrete construction. Versatility of concrete is one of the reasons why it's endured as a means of construction over the centuries. Its evolution has been informed by the demands of the way we live or we want to live. It's also influenced by innovation from other forms of technology. Now, there are currently very many ways in which concrete is used in construction, as I'm sure you're aware, different types of products and forms and framing systems and solutions, cast on site or pre-manufactured or a combination of the two. So for this series, we've chosen just two examples of very different approaches to methods of constructing in concrete, both of which bringing with them added benefits in terms of resource efficiency and carbon savings. And the two that we have chosen are de- and reconstructable modular concrete systems and 3D printed concrete. So I'm going to introduce you to the presenters in a second, but after each presentation, there will be time for a bit of Q&A, hopefully to be able to respond to some of your questions. So as we're going along, please do submit your questions via that Q&A button at the bottom of the screen. So the following presentation is entitled De- and Reconstructible Modular Concrete Structures, and it's given by Glen Rust, who's R&D Engineering Lead at Laing O'Rourke. And I will introduce, I'll ask Glen to join us in a second. And he's going to be talking about Laing O'Rourke's new patented structural deframe system, which can be simply deconstructed and reused or reconfigured, supporting the principles of circular economy. Now, design for disassembly and reuse is pretty well recognized as one of the strategies for design and construction to embed more circularity in the use of material and construction elements in the built environment. It's a way of keeping elements of a building in use for as long as possible, which is one of those key principles of circular economy, to be able to optimize their value and their potential, and of course, thus reduce embodied carbon. Now, concrete is a very durable material. It's got the potential for a very long serviceable life, especially by comparison to other building components, such as windows and servicing equipment, lightweight cladding. And so the strategy for facilitating the reuse of a concrete structure, so keeping it in place while all those other shorter-lived elements can be removed, and so that they can be disassembled and reused, is an excellent one. And it's represented by the layered concept, which is a picture on the screen here. Most commonly what happens today is that all of that stuff may be removed, but the structure is retained and reused and optimized for a long length of time. There's a great example there on the screen as well, as there are very many of them around the country. But the approach that you're going to hear about today takes this one step further, and it applies the design for disassembly also to those long-lived structural components as well. Now, you're going to hear much more about that in detail from Glen, but if you want to find a bit more about concrete and circular economy in general, we have a developing resource hub for it on the Concrete Centre website. So I'm now going to ask Glen to join me on there. Excellent. Nice to see you, Glen. And I'm going to mute myself, switch off my camera and hand over to you. So hopefully I will stop sharing and you can share your screen.
So thank you for inviting me to present at this talk. As Elaine said, my name is Glen Rust. I'm the R&D Engineering Leader at Laing O'Rourke. I'm responsible for the structural engineering and sustainability activities. As a bit of background to myself, I'm an ex-design consultant. I spent nearly 15 years at Arup as a structural engineer. And then for the past nearly 6 years now, moved to Laing O'Rourke and have been working within the R&D department. And my principal focus has been on the development of our next generation structural solutions, and I'm responsible for the R&D activities around sustainability, which is particularly around decarbonisation, with a focus on concrete. So I'm going to provide a little bit of background to the systems, the next generation systems that we've been developing, and then focus a lot on the reuse and the deconstructibility element of it. Now, within the development of these and the thinking of our next generation systems, we wanted to move away from the image that you can see on the screen. Okay, so in the development of our next generation systems has been thinking about construction. And this is construction today, and it's hasn't really changed very much. You know, this image could have been taken 40 years ago, and we find that construction, particularly around structures and building frames, even with the advent of DFMA over the last 10, 15 years, still requires a lot of construction activity. And we've been really challenging ourselves as how do we move on from this, and how do we transition to a different means? So how do we transition construction from construction sites to places of assembly? And that's really been an underlying challenge of how do we move on from this kind of image of construction that you have on the screen. And so in the thinking about of the what next, the next generation systems, there's been a number of guiding principles that kind of helped us in our thinking and our development, and I'm going to run through those overlying principles to give you a kind of bit of background. The first has been, how do we transition to fully off-site manufactured solutions? How do we get rid of off-site or in situ construction, and how do we enable all the benefits of off-site construction to really be realized? We wanted to think about how do you maximize standardization of products, and this is not us advocating for rectilinear brutalist concrete building blocks. It's thinking about how do you maximize the use of a standard product or component. So if you take any floor plate of any, say, commercial office or building, you know, 95% of the floor plate could be formed through a standard rectilinear component, and then the areas of architectural expression or site constraint is where you have the kind of more bespoke engineered to order approach. And so we wanted to think about how do you transition to product-based solutions and standardization. And it's a bit like how one would use hollow core concrete planks. You know, they're a standard product. You can vary length, you can put some chamfers on. So thinking about standardization. We wanted to significantly improve on-site productivity. We obviously wanted a very low material efficient, low carbon solution. And that's been a key focus. How do we transition away from very simple, easy to build, easy to interface with flat slab type approaches? And how do we get back to more material efficient solutions and therefore lower carbon solutions? And then finally, how do we start thinking about enabling the circular economy? Now, these were systems that we've developed in-house, so we've had full control over these. And so we've been able to think about all of these underlying principles and really build them into the design of the technical design and the architectural design of these systems. And circular economy has not been, you know, 4 or 5 years ago, was never really a key driver, a key pull from clients, but it was something as we were talking through and starting to think about this, you know, we've got to enable reuse at end of life. You know, whether it's a value now, today, we should be future proofing what we're building, and how. So that's been an underlying principle of how do we enable this circular approach. And what we developed and have been developing for the past 4 years is a suite of products. The image you can see on the screen is our technical prototype of a system called D-Frame. It's a demountable frame solution, hence D-Frame. And it was a product solution that we've developed specifically for the commercial office or the retail airport sectors. It's a one-way spanning primary beam with one-way spanning rib slab, so material efficient. But we've developed it to be a fully precast solution. So there are no construction activities, there are no structural toppings. It's fully precast. So the components arrive at site from a factory in their complete state, and we erect it very rapidly and then connect it all together with steel connections. And it's been that change of philosophy of connection, instead of just pouring an in situ monolithic topping slab to tie everything together, and by thinking about actually building on what the steel industry does, steel connections, that's allowed us to start thinking, right, it's steel connections, we can now think about unbolting steel connections. And then at the moment we have an in situ grouted joint, because we're not quite, we haven't had the time and the brain power to come and figure out a dry joint between all the components at the moment that deals with fire and acoustics. So at the moment we have a grouted joint and steel connections, and we achieve all of the structural requirements of a building, from diaphragm behavior, robustness, serviceability, and strength, etc. So that's the principle of the system, and we've got a range of these systems now. This is D-frame. We've got a sister suite called M-frame, which is more suited for the residential sector, where big primary beams and downstand ribs are not suitable, where you're trying to compete in a market of very thin PT slabs and tight floor to floors. So this builds upon the same principles, solid precast elements, but building that to each precast element, one component, one slab plank becomes one entire room. Downstand ribs can then be coordinated and built into internal partition lines, and we start tying again all the planks together with steel connections. And this is a prototype of that residential solution. And we've been building that approach, that product-based standardized approach up, and have just recently completed our third prototype that starts pulling this all together. This is a bit of an oddity of a prototype, because in this one little demonstrator building, we've built out an entire standardized school classroom and corridor elements, and a one bedroom apartment building in one demonstrator, hence the weirdness with regards facades and parapets. But it's demonstrating not just the structural deployment of these kind of solid precast solutions and products, but the whole package, so including facade elements, internal fit out, architectural fit out, internal services fit out, etc., and how you bring them all together. Now, from going back to the structural element, now we have this kind of standard chassis, so to say, of a structural approach, it's also allowed us to start adding products to that set. And so we're starting now to be able to further reduce the carbon in these. So this is a timber concrete hybrid slab plank. So it's a direct replacement to the fully precast one, in which we're starting to think about material use in a different, more hybrid way. So using materials where they're best suited for their materials characteristics. And so this essentially, the spanning slab tension concrete has just been replaced by structural CLT produced in Scotland, and it works in a composite hybrid manner. So we have this chassis of a system, and we're now starting to think about the product sets that can come into this. So that's an overview of a very brief overview of D-frame and a suite of fully precast frame solutions. And I think now, really building on the purpose of this talk and thinking about disassembly and reuse, I want to just touch on some of the key areas that we were considering, have been considering and investigating, and some of the key challenges that we've not unearthed, but starting to get a grasp of it, that we need to deal with when we start deploying reusable structures more widely in the built environment. So the first area that we really tackled with right at the beginning of our development was really the basis of design. What is the design approach one wants to take? Do you optimize a product, a component to the nth degree for its very specific use case, and you drive out every piece of material that's not required in it to get to the lowest carbon solution? Or do you design for future flexibility and reuse? So do you provide some over design? So, you know, if you think about commercial offices, you know, do you design for the minimum code 2.5 kPa live load, or do you design for a more kind of current approach of 4 or 5 kPa live loads, but that will allow you a better opportunity to reuse in the future? And that's it's a debate we're still continuing to have it both internally and with our design partners, our design consultants, as to what is the best approach to take. And I think we're currently settling on designing with sufficient load capabilities and capacities that you can use it in the future in different configurations or even in different buildings. So trying to maximize this use, because you're producing a piece of concrete emitting that associated emissions, and really you want to get the best use of that material. And then thinking longer term, I don't want to find that I can't reuse components so readily because they've been designed for a very, very specific use case. And we find that for most of our buildings, most of the loads and most of the use cases, this is absolutely applicable. And it's not just the basis of design from a structural capacity perspective, but it's also how do we accommodate architectural requirements both now and in the future. So going back to we're not advocating concrete brutalist building blocks. You know, this standardized product, you want standardized products that have the capacity to be aligned with alternative, more bespoke and special products. So much like, you know, very bespoke Lego components, you know, you buy specials and engineer to order components, but they all share a common connection typology. And that's very much an underlying principle that we want to take moving forward, that allows for a lot of flexibility in current use and deployment, but also in future use and reuse. The connections from a structural engineering perspective, one can obviously see are an absolutely critical part of the thinking and the design and the approach. The concrete elements are actually very, very simple rib slabs, very simple reinforcement cages. You know, they could have been designed 40, 50, 60 years ago without any problem. I think it's the connections and the thinking about that. How do you specifically design them to deal with all of the requirements of engineering and performance and robustness and fire, but that still maintain that disassembly aspect? And what we found in our approach, and it was really by chance, is that we really got the reusable aspects for free. We had to have a steel connection to connect everything together, and so it ended up naturally being a bolted connection because it aided our assembly processes, rapid assembly. We were challenged by this from a commercial aspect of why are we spending money to design for reuse? It's not required 4 or 5 years ago. And when we did a counter design of the steel connections, we found that actually designing with a countersunk bolt in these details actually worked out almost commercially negligible. You know, you're talking 10 or 20p a square meter for a building just to provide that capability. So to us, it seemed absolutely obvious that you would provide that capability because you can, and it's essentially you're getting it for free. Now, there were aspects in which we had to think about the fundamental engineering far more carefully and go back to really first principles, and had to go through a level of physical testing to prove principles and ensure that we were getting the kind of failure modes that one would want. Concrete fails in a very nice ductile manner with large cracking, so you can see there were issues. And that's what we wanted to maintain. So we've undertaken a number of tests and trials to really validate that engineering approach that we've taken. And that really leads on to robustness of which has been a key area of investigation for us, and it continues to be. We're currently coming to the end of a sponsored PhD at Imperial, looking at very specifically this, because we don't want to repeat the mistakes of the past. And when you have fully precast systems, you don't have monolithic structural slabs that are easy then to distribute load and provide that robustness. You're taking all of those robustness tie forces into specific connections, so they have to be thought about that. You have to think about how failure modes and column loss happens. We've started to realize the limitations of current codes when it comes to column loss approaches and the potential for under design when in column loss. So we've been doing a lot of work with Imperial University and others thinking about that. And then where you're taking loads and concentrating them, you've got to think about very carefully, and we've had to think about both the redistribution but also that concentration and the magnitude of that loads. And these are the primary beams for that D-frame solution that I showed the image of at the very beginning. And this would be very easy to build with an in situ. You could do a precast shell beam, put as much reinforcement as you wanted in that shell beam, pour an in situ stitch, and you've got a very easy, robust beam. I think when you come to trying to maintain that disassembly and unbolting ability, it becomes a little bit more complex because you're starting to deal with very large loads. And for this 700 deep beam on a 9x9 grid for a 5 kPa office load, you're dealing with nearly 2 meganewtons of tensile load that you need to deal with in a ductile manner to be able to get to a kind of catenary state to accommodate column loss. So again, we've had to scale up some of the physical testings to start validating some of the research we're undertaking at Imperial. So that's really been thinking about the design for current use, and then moving on to the disassembly. How does one go about unpicking the structure? And that's again been a key part. So we know with the bolted connections, we design them to be unbolted. We can call out where we're grouting bits in, and where we've got grouted joints, we're only dealing with very low stresses of diaphragm behavior, etc. So we've been able to use very low strength grouts, really actually designed for those specific diaphragm stresses, and get down to very small grouted joints, very low strength grout that starts to enable multiple ways of disassembly. And we can come along for disassembly and disassemble with either hydro demolition, which if we hadn't had a very low strength grout would have resulted in this image on the right, where you end up destroying half the product and half the slab, but not just taking out a bit of joint. Or we can just simply saw cut out those joints and then unpick the disassemble the frame and then go and refurbish those ready for reuse. So the disassembly and the methodologies, the practical methodologies, have been a key part of that. And really, I think we've got to a stage where the disassembly is as quick and easy as the original assembly. So there is no way in the future that you would come and demolish it in a traditional way, because it would be safer and quicker and cheaper just to unstitch it. And that really then, it's not just the structure, and Elaine touched on this in her introduction. We started to think about how do you then interface with all of the other internal fit outs and products, and how do you start disassembling those. And actually in lots of conversations we've been having with our demolition supply chain, actually the demolition industry is very sophisticated these days, and have been driven that from a commercial and landfill tax perspective to actually strip out buildings and maximize the amount of reuse and recycling of all of the components. So, they will specifically build into their processes and their methodologies of having people, taking out carpets, having a reuse supply chain of carpets will come and collect their products, and they get a commercial benefit by somebody coming to collect carpets and other parts. So the demolition industry is already quite sophisticated and tracking along this. And so you would then get to the kind of monolithic frames, and you end up just demolishing them and then downgrading their value and using them for subbase and aggregates and that. So So we've got been given quite a level of comfort that actually the internal fit out is being dealt with from an MEP services perspective. We believe there'll be a much more of a transition, much like the aerospace and automotive industries, to a leasing type model. And then the structural frame, we've now started thinking about the reuse elements of that. And when you come to reuse, it's how do we actually go about the reusing? So we've disassembled them, but how do you reuse a component? And as an ex-design consultant, and many people out there will have worked on refurbishment jobs, you know, you go to an archive room, get a box of structural drawings from the 1960s, half the information's missing, you don't know what they were designed for, what's in these elements, and you end up doing a whole rake of destructive testing, and just to understand the basis of design, and a huge amount of time and effort goes into just understanding existing buildings. So we've been starting to think about how do we embed that information directly in the components. So we started with simple embedded RFID tags that link then to Excel databases with all that information. But there's not a concern, but there's the thought of what happens if it's an external database that holds all that information. Who holds that database? How do you track that through a 60-year life or more of a building? So we're starting to investigate technologies that are a little bit more sophisticated, in which we can embed much more information than a simple RFID tag, where we can start embedding the material properties, the design characteristics of those components, and then embed those two embedments within each component, so that we start thinking about material passports being part of the products. And this is really enabling, there's a lot of research come out of John Orr at Cambridge and others about buildings as material passports and enabling the circular economy. And that's then, you know, we've then got to think about, and this is a big challenge to the industry moving forward in the future, is how do you scale up what we now understand, you know, is craft, kind of architectural salvage. I'm refurbishing my house, I want, you know, nice tiles or salvage timber or tiles, etc. How would we work and operate as an industry when you're scaling that up to entire building components, whether that's structural steel or concrete? And there needs to be a lot more sophistication in the automated identification and kind of asset cataloging of assets in a way that we can, as engineers and design consultants and contractors, use reused buildings. So how they are catalogued, how they assessed, how do they get deployed into kind of more generic designs in a very efficient manner that allows me as a contractor to then start using reused materials in the future. And I think that's a key area of focus. There's a lot of academic research. Dr. Daniela Densley-Tingley at University of Sheffield is starting to doing a lot of work around this, and we're trying to support those activities and that research with our industry expertise. And then finally, what's next? For us, you know, we've got now a platform, so to say, of a system, a structural system, and we've been building upon those principles. So we've been recently collaborating with Arup, designing a compression shell. We're just manufacturing a prototype at the moment, ready to be assembled, which takes the same principles: fully precast steel connections, disassembled, demountability. And starting to get to very, very low carbon systems, where we're targeting an 80% reduction on embodied carbon compared to the kind of commercial office frames that we're currently delivering today. So these principles, once we've got our heads around them, are very applicable, not just to the system we currently have, but to all our future systems and development and collaborations with design consultants. So I'm going to stop there and then stop sharing my screen and open for some questions.
Thank you very much, Glenn. Well, a very thorough look at all of those issues. And we have got a few queries here, but unfortunately, I think we're running a little bit short of time. So I'm just going to pick one, and maybe you can answer them
Sure.
online.
Sure.
It was a little bit more about the joint itself. and how you envisage that that mortar joint could then be disassembled. And I imagine that that's the principal area that potentially would concern for longer term durability or the fire issues with regards to that, because that's the change. Could you just briefly maybe talk about that?
Yeah, so the steel connections, we've undertaken a full fire engineered approach to them, so we understand how we deal with them from a fire perspective. That D-frame, actually, the joints are only there for robustness. The system, you can take all those steel connections away and the system still stands up. So in that particular scenario, we don't need any fire protection because you don't have this concurrent robustness and fire. In other systems, we do require fire protection. The steel joints, the steel elements are unbolted. We do have an areas where we core out in the embedments, so we don't, and it's much like the grouted joints. We're not stating that we save every piece of material that gets built within the superstructure. There is a level of area, such as the grouted joints, that we can't reuse, that essentially get saw cut out or get cored out. But the principle is we try to minimise that to a small, very small magnitudes, less than 0.5% of the volume of concrete or cementitious material we're using, and it's the main components, and we can core those out and refurbish them pretty easily.
Brilliant, brilliant. Thank you very much. So thank you ever so much for that presentation.
Sure.
Really, really excellent work, and I've got tons of questions as well. I'll have to.
Sure, I'll answer the questions in the chat.
That's lovely. Thank you very much.
Thanks, Elaine.
So thank you very much, Glenn. That was an excellent presentation, as I said, and some really great questions that have been asked. And please do look out for other recordings in this Fresh Concrete series that are available on the Concrete Centre and the Building Centre website. There is so much innovation going on within this field, and it's excellent for us to be able to share with you some of the innovation, not just happening within the world of the construction and the way that concrete is put together, but also in its manufacture, the concrete itself, and potentially different uses for concrete as well. So please do stay in touch and look at some of these other recordings. Thank you.